there exists a difference, again, a difference between numeral system expressing finite numbers and numerals expressing infinities. In fact, we use the same numerals expressing finite numbers. In all the situations, we need these finite numbers. In contrast, different symbols are used to work with infinity. For example, in standard analysis, we use this symbol. When we work with the Cantor's ordinals, these symbols, with cardinals, these symbols, then in non-standard analysis, you can talk about generic infinitesimals, so generic infinites. So our second goal is to develop such a numeral system that the same numerals could be used in analysis working with functions that can assume different infinite, finite, and infinitesimal values for measuring infinite sets. And in general, in all the occasions, we need infinite and infinitesimal numbers. So we would like to do this in the same way as people do it with finite numeral systems. A few words about different finite numeral systems. They can express different sets of numbers and can be more or less suitable for executing arithmetic operations. For example, even if the powerful positional system is not able to express by a finite number of symbols irrational numbers, for example, pi. So, in fact, this numeral is deliberately introduced to express the desired quantity. I remind you that we would like to execute practical computations, so we need numerals that contain a finite number of symbols. So if people would like to work in the positional numeral system with irrational numbers, then they use approximations. And there exist numeral systems that are weaker than the positional one. For example, Roman numeral system is not able to express zero and negative numbers. And such an expression, for example, like this, 3 minus 5, is an indeterminate form in this numeral system. So Romans were not able to say a word about zero and negative numbers and to create mathematical knowledge, including this concept and these numerals. So numeral system limit our possibilities not only to compute, but also to produce theoretical knowledge. And it is interesting that if we substitute Roman numerals with positional numeral system where there is zero, where there are negative numbers, then this philosophical problem that exists in Roman numeral system, what is the result? 3 minus 5, because it is inexpressible. The result is inexpressible in numeral system. It disappears, and we just compute without thinking about it. And there exists even weaker numerals. For example, the unary numeral system is the system where a number n is represented by n strokes of people. For example, 5 written in the positional numeral system in this unary system is like this. And clearly that it is extremely difficult to execute arithmetical operations in it, just because of the practical difficulty. For example, I am not able to count what is this number because all these strokes are so similar. And we cannot in this system write down huge numbers. And it is not clear how, for example, to divide this number by this number in this numeral system. Probably people using this system of writing down numbers even did not know about division. We do not know. And strangely enough, there exists even weaker numeral systems. Nowadays in Amazonia, there is a tribe of Piraha. They use only numerals this one and this one, so 1 and 2 strokes, to express numbers 1 and 2, and they do not suspect about existence of other natural numbers. So all quantities larger than 2 for them are just many, and such operation as 1 plus 2 and 2 plus 2 give the same result, many. Obviously, this happens not because 1 plus 2 is equal to 2 plus 2, but because the system is too weak to see the difference. And pay attention that the result many is not wrong. It is not accurate. For example, if you ask me how many trees there are in the garden in front of my house, I will answer many. This is a correct answer, but with a low accuracy. Why I'm talking about this? I wish to talk about infinity, but I'm talking about because in the numeral system, many plus 1 is equal to many, and many plus 2 is equal to many. And these two records are very familiar to us in view of our traditional views on infinity. In fact, if we substitute many by infinity, we can see immediately that we have exactly the same situation. On the other hand, we know that if many is substituted by numerals 3, 4, and 5, then we are able to avoid this strange kind of records. So probably by introducing more numerals that can be used to express different infinite numbers, we can avoid this kind of situation. And it is interesting that close to Piraha in Amazonia, there is another tribe, Munduruku, that is able to distinguish numbers up to 5, and they have too many, some not many, and many really many. And this again is very close to the arithmetic of cardinals of Cantor. So you see, if you substitute some not many by aleph 0 and many really many by aleph 0, then you have the same result. And I remind you that we have the Cantor set theory in the foundations of the modern mathematics. So this advises us that introduction of more different infinite numbers could allow us to avoid this kind of records and to make our results more precise. So it is clear that methodology of working here that we are going to start to discuss is different with respect to the traditional methodology applied for working with finite numbers. So we would like to introduce this methodological postulate. So we postulate existence of infinite and infinitesimal quantities, but also we accept that human beings and machines are able to execute only a finite number of operations. So a priori, we accept that we shall never be able to give a complete description on infinite process and sets due to our finite capabilities. And this means also that we accept that we are able to write down only a finite number of symbols. Now, the second methodological postulate comes to us from physics. In natural sciences, when a physicist looks in a microscope and observes two dots, he or she does not say that the object of the observation is two dots. He or she says that with this microscope and this lens, I observe two dots. So they talk about what they observe and not about the object, because they perfectly understand that there exists object, instrument of the observation, and the researcher. And we are not able to touch directly the object. We need an instrument. In fact, probably if we substitute the first lens in our microscope with the second one, then the first dot will be visible as 10 dots and the second dot as 15 dots. Again, can we say that this is our object? No. 10 dots and 15 dots are results of our observations with the second lens. Now, a natural question arises: which answer, 2 dots or 10 and 15 dots, is correct? Both, but with different accuracies. So physicists always, when they give an answer of an observation or a measurement, give also the accuracy of the used instrument. We will do the same. We will follow natural sciences, and we shall not tell what are the mathematical objects we deal with. We just construct more powerful tools that will allow us to improve our capacities to observe and to describe properties of mathematical objects. So we always will separate mathematical objects with the tools used to study objects. And we accept that different tools will give us results of observations with different accuracies. So what are our tools? What mathematicians use like tools? Mathematical languages and numeral systems, among other tools. So we will concentrate, in fact, on numeral systems, systems allowing us to express numbers. So we have already seen that these records, many plus one equal to many, is the result of the poor numeral system. So we should, in some way, to be able to register that if we add one to an infinite quantity, we should have more than the previous infinite quantity. Obviously, we cannot use these symbols. We should introduce some other numerals to work with them. By the way, Euclid, in his common notion 5, has formulated like the part is less than the whole, and we will use this principle in all our counting, and we adopt it for working with all numbers, finite, infinite, and infinitesimal, and with all certain processes, finite and infinite. Now, I would like to say that in mathematics, numbers are introduced in logic like the result of the operation of 1 plus 1 plus 1 plus 1. However, when people count, they count in more complex ways. They not only add unities, they also often use different units of measure. They subtract from a given quantity, or they divide a given quantity in its parts. And now I would like to show you a way of counting that exists on the Earth for thousands of years, but strangely enough, it has not been formalized in mathematics so far. And I will try to convince you that this way of counting is much simpler and much more powerful with respect to the traditional ways of counting. Okay, this is exactly what I was saying on this slide, what I have just said. So let us consider this example. So suppose that we are in a granary and the owner asks us how to count how much grain he has inside. Obviously, people are not able to count seed by seed because there are too many objects. And the question arises how such enormous number of objects to compute in a reasonable time. Clearly, we can say that there are many seeds in the granary. This is the correct answer, but its accuracy is very low. So, in order to overcome this difficulty, people take sacks, fill them in with seeds, and count the number of sacks. Obviously, we suppose that all sacks, in this example, all sacks have the same measure, and all seeds have the same measure, and each sack can contain the same number of seeds. Unknown for us, because we are not able to count even how many seeds there are in a sack. If the granary is huge and it becomes difficult to count the sacks, then trucks or even big train wagons are used. So again, we do not know how many sacks there will be in one truck, but we know that each truck contains the same number of sacks. And we do not know how many trucks will be in one train wagon, but we know that each train wagon contains the same number of trucks. So at the end of counting, we obtain a result in the following form. The granary contains 17 train wagons, 12 trucks, 15 sacks, and 54 seeds of grain. Look, this answer has the accuracy of one seed, because now we can, for example, add one seed, and we will see that we have not 54 seeds, but 55. If we subtract one track, we will see that we have not 12 tracks, but 11 tracks. So we have obtained the result with the accuracy of 1 seed of grain. Let us discuss this example a little bit more. So in this example, it was necessary to count large quantities, even though they were finite, but people were not able to count them using elementary units of measure, seeds. And so they have introduced new units of measure and behave with them as this new unit of measure were infinite. So these new units of measure are sex, track, strain, vacancy, and it is possible to continue. Thus, it was impossible to formulate the answer in the terms of elementary units of measure, but it is perfectly expressible in the newly introduced system of counting. And I would like to stress that we do not count how many seeds are in a sack. We are not able to do this because there are too many. We do not count how many sacks there are in a track, how many tracks there are in a train wagon. So each new unit of measure contains a certain number ki of previous units, but these numbers ki are unknown. In spite of this, we are able to introduce these new units of measure and to express the desired quantity by these new units of measure. So it is clear now what I would like to do. I would like to extend, to generalize this way of counting with huge but finite numbers to infinite quantities. So let us do it. We will introduce more numerals. We will enrich our language. So it is clear now what I would like to do. So we have introduced our postulates, and as a result, we are not able to use such concepts as bijection, numerable sets, continuum, and to use these symbols. Analogously, when we pass from Roman numerals to the positional numeral systems, these symbols are not used. However, there will be no any contradiction between the new way of doing and the traditional one. The situation will be exactly like with the microscope or telescope, if you like, with the two lenses. There is a lens of Cantor, there is a new lens, and I will show you that the new lens in certain cases allows us to obtain more precise results. So how will we do this? You know that there exist axioms for real numbers, and we will add a new axiom and I will show you that of the infinite unit. It will be expressed by this number, one circled, called gross one, and it is introduced as the number of elements of the set of natural numbers, and it is defined through its properties. So this is exactly the same way how we move from natural numbers 1, 2, 3, 4, 5, and so on to integer numbers, where there are naturals and also 0 and -1, -2, -3, and so on. So how people do this? They take axioms for natural numbers and they say there exists an object called 0 and expressed by this symbol. Operations with this symbol are like this and like that, and then we obtain a nice and powerful arithmetic with integer numbers. Here we'll do the same. We introduce this symbol and we'll show how to work with it. So first, property is very simple. This property is infinity. So gross one is the number of elements of the set of natural numbers. It is infinite. So it should be larger than any finite natural number n. Then gross one is a number. So 0 multiplied by gross 1 is 0, gross 1 minus gross 1 is 0, and so on. I'm telling this because when we work in the traditional analysis, we have indeterminate forms of the form infinity minus infinity or 0 multiplied infinity and so on. In our analysis, we'll avoid this kind of indeterminate forms. Analogously, when we have introduced 0, we have avoided indeterminate forms of the kind 3 minus 5, because we are able just to compute directly without any problem in this way. Now, the most interesting way of counting and the property is divisibility. So think about the set. This is the set of natural numbers. Think about it like about our SEC that has gross 1 seeds. So the set of natural numbers we postulate has gross 1 elements. Then we postulate that this set can be subdivided in 2 equal parts, and each of them contains gross 1 divided 2 elements. Pay attention, we are not able to count 1, 2, 3, 4 elements of these two sets, because due to postulate 1, we are able to execute only a finite number of operations, and these two sets are infinite. Here we apply in the strong form postulate 3. The part is less than the whole. Here we say that half of the set of natural numbers is exactly 2 times less than the whole. So we are not able to count how many elements there are in the set n. We are not able to count how many elements there are here and here. But we are able to say that in our SEC there are 2 times more elements than in half of the SEC. So we apply, as I promised you, people count in a more complex way than just adding 1, 1, 1, 1, 1. Here we take the whole and we subdivide it into equal parts. And then it is possible to subdivide it also in 3 equal parts. And each of them will have gross 1 divided 3 elements. These sets will be very useful for us. So what is this? This is the third part of the set of natural numbers starting from 1. 1 plus 3, 4, 4 plus 3, 7, and so on. What is this set? This is the third part starting from 2. 2 plus 3, 5, 5 plus 3, 8, and so on. And in general, we suppose this is that the set of natural numbers can be subdivided in n parts of this kind, and each of them contains this number of elements. We can immediately start. By the way, so I have shown you how to compute. These ways of computing have been studied by professional logicians, showing that it is not contradictory. And also it is possible to see who is involved in non-standard analysis stuff, why what I'm saying is not non-standard analysis in this case. Okay, now let us measure infinite sets. It becomes extremely easy. For example, how many elements there are in this set? It is easy to see that this is the 5th part of the set of natural numbers starting from 2. 2 plus 5, 7, 7 plus 5, 12, and so on. So it has this number of elements, gross 1 divided 5. How many elements we have in this set? Also easy. This is the 10th part of the set of natural numbers starting from 3. 3 plus 10, 13, 13 plus 10, 23. So it has this number of elements. And we are able easily to execute set theoretical operations with these sets and to compute the result, how many elements there will be, for example, here in this set. This is easy. Intersection of these two sets is empty. This is easy to show. 2 belongs to the first set, 3 to the second. So what we have done, we have added 2 new elements. So the first set, this one, has gross 1 divided 5 elements, plus gross 1 divided 10 elements, because this set has gross 1 divided elements, plus 2 new elements. So this is the result. And we can write down and interpret many other numerals. For example, what is this? Gross 1 minus 2. From the point of view of the granary, this is the number of seeds in a set from which we have taken out any 2 seeds. From the point of view of the set theory, this is a number of elements in the set of natural numbers, from where we have taken any 2 numbers. What is this? This is 6 tracks minus 2 secs plus 3 seeds. In order to interpret what is gross 1 square from the point of view of set theory, it is sufficient to think about the set of couples of natural numbers, you see. And in fact, this is the first couple, the second, the last one in the line. This is the first in the column, the second, the last one. So gross 1 lines, gross 1 columns, and gross 1 square is the number of these elements. Okay, so we have introduced gross 1 as the number of elements of the set of natural numbers. We extrapolate from finite to infinite this idea that the set 1, 2, 3, n minus 1, n has n elements. So gross 1 is the last. So we have introduced gross 1. Gross 1 is the last natural number because it's the number of elements in the set of natural numbers. In the same way, in the set from 1 to n, n is the number of elements. So now we are able to observe infinite natural numbers. And if you have a difficulty to accept the existence, this is because traditional numeral systems did not allow us to see these numbers. Again, Piraha are not able to observe numbers 3, 4, and 5 by they are via these numbers. And if we introduce more numerals, then we are able to work with them. Now, I would like to stress again with this simple example the importance of separation of objects, mathematical objects, and mathematical tools. Suppose that our object is the set of natural numbers, and we would like to observe it using a very weak numeral system that has 1, 2, and gross 1. So, among natural numbers, we are able to observe only these ones. 1, 2, gross 1 minus 1 minus 2, gross 1 divided 2, plus 1 plus 2, minus 1 minus 2. That's it. And now, dots have a very clear meaning. They represent numbers that are not expressible in this weak numeral system. Now, what will happen if we will execute the operation 1 plus 2? What will be the result? Piraha would say many, but we know that here first we have the numeral many, or quantifier many, if you like. And then we have gross 1 minus 1, and only this. So we are not able to express the answer 3. And the correct answer to the question, what is the result of 1 plus 2, is this numeral system, only with these numerals, is too weak to express the result. We need to express more numbers and to introduce a stronger numeral system. So instead of saying that this is a huge and difficult mathematical problem, we say our instrument is too weak. It is not inadequate for this problem. It is necessary to substitute the instrument. So methodologically, I guess that this is a very powerful idea that physicists have understood more than 100 years ago. So it is not necessary, and it is dangerous. It can lead to ambiguities, to identify the used instruments, numeral system in this way, and the studied object. It is necessary to separate them. Now, so we know that from 1 to gross 1, we have natural numbers. Then we have seen also that there exist numbers larger than gross 1, and here there are many of them. So they belong to the set of extended natural numbers. How many elements has this set? The numeral system with gross 1 is too weak to answer to this question, because any numeral system, including the system with gross 1, has its limitation and has numbers that cannot be expressible in this. In fact, when I have introduced this symbol, 1 circle, this is a prompt that can be gross 2, gross 3, and gross and so on, that can be introduced in various ways. Now, let us return to the computer. We would like to compute to construct a computer, and we will use a positional numeral system to express our numbers, because we need to store in the finite memory of the computer our infinite and infinitesimal numbers. So this is our record, our number, and as in any positional system, it is the sum of different powers of the base, in this case gross one. So C are called gross digits, and they represent how many, which part of each of the powers of gross one, the sum of different powers of will be included in our number. So gross digits can be positive or negative, and they express finite quantities. Then there are gross powers that are ordered, and also they can themselves be of this kind. Now, in order to understand what is this, let us suppose to consider the first simple situation. We have no positive gross powers and we have no negative gross powers, so all this record is reduced just to this. I remind you that gross 1 powered 0 is 1, so everything is reduced to this. And so we have here just C, and C, I remind you, C, all C are finite. So the finite numbers are just simple examples, particular cases of this record. If we have here finite or infinite positive gross powers, then in our number there can be different parts, infinite parts. If in our number there are negative finite or infinite gross powers, then there can be different infinitesimal parts. So in the finite case, we work in the positional numeral system without thinking about whether there are in our number hundreds or thousands or units. We all elaborate all of them in the same way. Here we will do the same with different infinite and infinitesimal parts. We will not think about, it is not important here, there are infinite parts or not, how many there are. They all are elaborated in the same way. And if there are no finite or infinite parts, then we will have infinitesimal. The simplest infinitesimal is 1 over gross 1, that is inverse element with respect to multiplication. And all infinitesimals are not equal to 0. For example, this number is positive because it is the result of the division of one number, positive number, by another positive number. And infinitesimals also can be interpreted from the point of view of granary, because what is the gross one? It is the sec viewed from the point of view of single seed of grain. And what is 1 over gross 1? Seed viewed from the point of view of the sec. Now, in order to show you how to execute operations, I will show you this toy application. This is an infinity calculator that allows us to operate numerically, so with floating point numbers, with different infinite and infinitesimal numbers. Behind it, there is the infinity computer. So this is only simple operation. I will show you how to compute. Let us start. The first example will be simple. So this is an infinite number because it has this positive finite gross power, and it is necessary to take 14.8 parts of these kinds. We would like to sum up it with another positive number that also will be infinite. Positive finite gross power, and it is necessary to take. Let us compute. So the result is this number, it is infinite number having two infinite parts. If we subtract, the second operand will go with the sign minus. If we multiply, then we have we should sum up the gross powers and multiply gross digits. So we have this infinite number. If we divide, then gross powers are subtracted and gross digits are divided. Obviously, this is a very simple example. Let us make things more complex. Let us introduce a finite part in our number. I remind you that it should have gross power equal to 0 and an infinitesimal part. Gross powers are subtracted and it should have a negative. Obviously, this is a very simple example. Let us make things more complex. A negative part. So in this number, we have one positive part, one infinite part, one finite part, and one infinitesimal. If we sum up, then we obtain the result having two infinite parts, one finite and one infinitesimal. If we multiply, all gross powers are summed up and all gross digits are multiplied. So this result is an infinite number having three infinite parts. And if we divide, then we have as a result a number having one infinite part and two infinitesimal parts. So we have a computer and we can use it to solve problems. I will show you just one problem. So suppose that we have a function g of x represented by a computing procedure f of x, and we would like to compute its derivative, but we have no problems. We have no, unfortunately, the computer program to allowing us to compute this derivative. So people use this approximation formula. If we are in mathematical analysis, then taking limits of all these expressions, if f is differentiable, then they will give us the first derivative. But on a computer, this is not the case, because when h becomes very small, then in the numerators we have the same numbers, because the number of digits in mantissa in the computer is limited, and we will arrive to the situation where it is not possible to compute. There are errors. I just illustrate this by using this function, and we would like, it is represented by a computer procedure f, and we would like to estimate using this formula its derivative with the point 3. So here we have forward and backward differences, here central difference. On the horizontal line we have h, and here on the vertical axis we have error. So when h becomes smaller and smaller, then error initially diminishes, but then when this situation with mantissa occurs, what happens? It happens that the error goes to the sky in all these cases. So it is a problem that on traditional computers it is not possible to avoid. What if we go to on the infinity computer? On the infinity computer, the situation is is different, because we can avoid using this dangerous formula. Suppose again that we have this function, it is represented by procedure f of y, and we would like to compute not only the first derivative, but also the second and the third derivative at the same point. In addition, we suppose that we do not know the formula. It is a black box for us. So instead of using those formula, we just evaluate f at the point 3 plus this infinitesimal value. What the computer will do, it will take this number and will assign it to x, and will execute this operation. But for us, it is a black box. We are not able to see this. So what we are able to see, we are able to see only the result. The result is a number having one finite part and several infinitesimals. Now, look what happens. It is possible to prove that if we take 2, then it will be the exact value of the function at point 3. If you take minus 0.5, it will be the exact value of the first derivative. If you take 0.25, it will be the exact second derivative. multiplying it by 2. So, and this minus 0.1 gives us the exact third derivative. So, we are able on the infinity computer to obtain exact values of the derivative just by one evaluation of the function. So this is really amazing. Now, let us now say a few words. I am close to the end of the lecture about some arithmetical paradox. So suppose we are in the traditional viewpoint, traditional fashion. Suppose that we have x, we multiply both parts by 2, then we add 1 on the left and on the right. So what do we have here? We have x. We can substitute. We obtain 2x plus 1 is equal to x, simplify, and obtain x equal to minus 1. But our x is this one. So you see, traditionally, we obtain this result. Here there are no errors. That the sum of an infinite number of positive integer numbers is equal to minus 1. Of course, you can say that this is a series and it is possible to do, it is necessary to behave another way. However, this result is considered seriously and as a correct result, because we have done all the traditional steps we do when we work with the finite quantities. In the new fashion, new methodology, what can we say? This result is